planet Earth as seen from space in the last quarter of the 20th century. From here, no one would ever guess that there are over 4 billion human beings attempting to live together down there. And every day, an additional 211,000 babies come into the world to join them. At this rate, the Earth's population will more than double by the year 2013. It's hard to see in our daily existence, but the Earth is essentially one enormous ecological system, exceedingly complex, with infinite numbers and varieties of interrelated and interdependent parts. The quality of life here, indeed our very survival, depends on the preservation of the system. We must find ways to use it wisely. In this context, the Space Shuttle may become one of the most important tools of our time.
Switching command to internal. Fuel tank pressure 61.5 degrees. Minus 130. Securing on tank for minus 125.
Ready to go. Coming up on the 10-second mark. 10, 9, 8, 7, 6, 5, 4, 3, 2. We have ignition.
As the first 2 decades of the United States exploration of space drew to a close with the Apollo lunar program and manned space labs orbiting the Earth, our government, along with top scientists and engineers, formulated plans for a new era in space. We could no longer afford to throw away the basic transportation system used to achieve a mission. We needed a reusable vehicle that could make flights into space routine. The result was the Space Shuttle. It is in essence a carrier of cargo, a mover of freight, much like a train, ship, truck, or plane, transporting men and equipment into near-Earth orbit. At launch, the shuttle consists of the orbiter vehicle, about the size of a 727 aircraft, a large propellant tank, and 2 recoverable solid rocket boosters. By the time the orbiter reaches orbital altitude, the solid rockets and external tank have been jettisoned. A typical mission will last 1 week, but can be extended up to a month. Following the mission, the orbiter re-enters the Earth's atmosphere and glides to a landing, much like a conventional aircraft. Within 2 weeks, the orbiter is refurbished and readied for another flight. Maintenance on the engine is similar to that practiced by commercial airlines. Each engine is designed to perform for 55 flights. While out in space, a shirt-sleeve atmosphere on board the shuttle permits scientists and specialists to accompany their equipment and experiments into space. No longer does a crew member have to be a test pilot in peak physical condition who must undergo an extensive training period. We've established what a space shuttle is. Now let's examine why we need one. High reliability and reusability are perhaps 2 of the most positive features. A single vehicle can be put to the task of launching many unmanned satellites during its lifetime. The cost savings is obvious over the present use of a one-time only launch vehicle. And if economy is important, and it is to all of us, consider the recovery of multi-million-dollar communication and weather satellites in need of repair. When they fail now, they just become inoperable space hardware circling the Earth. This single multi-purpose vehicle can, on other occasions, become the launch base for payloads with propulsion stages. These, in turn, can place satellites into higher orbit or send them out on an interplanetary journey. The improved satellites of the shuttle era will perform many jobs. Scanning devices circling high over the Earth will aid in our search for elusive and rapidly diminishing resources. With this information, geologists can locate new petroleum, natural gas, and valuable mineral deposits. Specially equipped cameras will become the first line of defense for our forests, detecting disease and insect infestation in its early stages. The same equipment can provide surveillance of waterways, lakes, and coastlines, monitoring pollution and its sources. Ships at sea can be forewarned of impending storms so they can steer a course to calmer waters. Likewise, on land, early warning of large weather disturbances like hurricanes can save countless lives. And for a hungry world where children still go to sleep with empty stomachs, sensor systems carried to space by the shuttle will monitor crops, tell of their vigor and probable yield, and warn of disease and insects. Oceanographers will better understand current patterns and temperature changes, so fishing experts can predict the movements of schools of fish. In the weightlessness of space, researchers can conduct experiments that would be impossible with the gravity on Earth. A boon to science, medicine, and industry alike. And the list is endless. When you figure that a single space shuttle orbiter can fly 100 missions before being retired, and each of those flights will carry a variety of payloads, all devoted to using space to benefit Earth, then you can see that the return will be many times greater than the investment.
Okay, so now we know what a space shuttle is and why we need it. That leaves us with how. How do we get it there? Because the shuttle is designed to perform a wide variety of missions, it requires an entirely new breed of rocket engine to propel it into space.
In the early planning stages, it was known that the engine had to meet certain criteria. It had to, above all, be reliable, for the most precious cargo would be human life. It had to produce high thrust, and yet be low in weight and very efficient. And it had to be reusable.
Rockwell International's Rocketdyne division, located in Canoga Park, California, where I'm standing now, was selected by the National Aeronautics and Space Administration to design, develop, and build the space shuttle's main engines. Rocketdyne has long been the leading builder of high-thrust liquid propellant rocket engines, including this largest rocket engine ever built.
To their proud credit are the engines that took men to the moon and back. And the engines that stood by, ready to propel intercontinental ballistic missiles in defense of our country. The one called the workhorse of space. And the early products. The ones that launched America's first satellites. From this, Rocketdyne reaped a vast amount of knowledge, and then drew upon that storehouse of experience to create the engine for the space shuttle. The shuttle engine burns as propellants liquid oxygen and liquid hydrogen. The exhaust is totally non-polluting. It is water vapor. The engines are movable during flight. This capability, called gimbaling, gives the vehicle directional control. At time of launch, 3 of these engines fire in unison. They provide the highest thrust for their weight of any rocket engine yet developed, and the thrust is variable from a minimum range to full power. The high pressures and temperatures experienced in this engine necessitate the use of materials and fabrication techniques totally new to the field. The combustor body, where propellants burn after being injected, is a slotted channel design made from a Rocketdyne-developed copper alloy called Narloy Z. Walling in of the slots is accomplished in this large, computerized electrodeposition facility. Coolant tubes form the engine nozzle. The tubes are brazed together in this gigantic gas-fired furnace. At Rocketdyne is the largest electron beam welding facility in the United States. The entire power head of the engine can be placed in this vacuum chamber. Over 200 major electron beam welds are used in the manufacture of the engine. Critical engine weight is minimized by using welded construction wherever possible.
Other key components of the engine are its turbopumps. There are actually 4 of them, and they are responsible for getting the propellants to and through the engine at the proper pressures and flow rate. The turbopumps are sophisticated, state-of-the-art, high-speed rotating machinery. They are assembled in ultra-clean rooms. The power potential of these machines is quite awesome.
For example, if water were pumped at the rate fuel is pumped by 3 space shuttle main engines, an average family-sized swimming pool could be emptied in 25 seconds. The fuel turbopump weighs about the same as a modern V8 automobile engine, but develops as much horsepower as 28 diesel locomotives. The high-pressure oxidizer pump delivers the power of 11 more. This is the first rocket engine to use a built-in electronic digital controller. Besides accepting commands from the crew of the orbiter, the controller will monitor engine operation, and in the event of a problem, will attempt to correct the condition. If this fails, the engine is safely shut down. The mission can continue with the remaining 2 engines. Testing of the engines is carried out in rugged terrain near Los Angeles, at the Rocketdyne Santa Susana Field Laboratory, and on test stands of the National Space Technology Laboratories near Bay St. Louis, Mississippi. Here also, the 3 engine clusters are test-fired. Only upon completion of stringent testing are the engines considered ready, and at that time they are delivered to Kennedy Space Center, Florida, for installation in the boat tail of the orbiter vehicle, where the entire system is readied for launch. The Space Shuttle, it is America's space transportation system. It is a versatile, reusable spacecraft capable of carrying single, multiple, or mixed payloads to and from space at economical cost. Shuttle Power. It will benefit America and all mankind in many ways. Not once or twice, but routinely to the end of this century and beyond.